Hello everyone. Let us talk about maximum a posteriori and maximum likelihood receivers. Maximum a posteriori and maximum likelihood receivers will be used for detection and estimation of certain quantities. To explain the concept, let us take a system described as y is equal to ax plus n, where x is some quantity which we need to actually estimate, y is the measurement done, a is the constant, a is some constant, and n is noise, which we, for the sake of simplicity, we will assume that it is AWGN, additive white Gaussian noise. So in this system, we will take measurements. So y, we will take the measurements of this quantity which is y, and we'll work out what is x. So and in the using the map and the ML concepts, we will work out what is x. Now, x can be a temperature in IoT device. If some IoT device is measuring temperature, so that can be x. X can also be um, so measuring it with amplifier. So what we are doing is that we are measuring the temperature in the user from an IoT device, and we are amplifying it, which is what A is here, which is what this A specifies here. A may be the gain of the amplifier, and N can be the noise in the amplifier, right? So X can also be another example of X can be, it is some digital data. In that case, A will be the gain of the channel and N will be the noise from receiver electronics. Now, third example can be X can be any grid coordinates in radar tracking, that where the particular object is located. So we can estimate the location of that particular object using the radar tracking also, right? So particularly Y are the measurements that we are doing, and X we want to estimate actually. Now, before we go to the map algorithm, we will first talk about maximum likelihood. Maximum likelihood function. So we have to estimate x. We will represent it with x hat, which is estimate of x, and so it will be a function of y. The point is that we have to estimate x. Now it will be a function of y. What are y's? Y's are the measurements that we are taking, right? And is equal to the argument of maximizing. Argument of maximizing means the this estimate will be equal to that value of x which maximizes this function. What is this function? This is fy y given x. This is actually the PDF of y given x, right? So we will say that we will represent in the case of maximum likelihood estimation, we will represent it with x hat, and it is a function of y, which are the measurements. So we have to look for, we have to actually maximize this function for all values of x, and for the value of x which gives the maximum of this function will be our estimate. So this is maximum likelihood estimation. Well, this is not so intuitive, intuitively this does not come in somebody's mind that this will be the estimation that we can make. So exactly what does it mean? We have to actually look into the details of this function so that we can in our mind we can understand what is the concept. So let's see what this function is. What this function means. This function, particularly the PDF of y given x, which is fy y given x, f subscript y given x. So PDF of y given x, that is, if you know what is x, so what is the meaning? Why measurements are conditioned over where x is given, right? Now, if you know what is x, what will be the distribution of y? So what is the meaning of this? If you know x, so what will be the distribution of y? That will be defined by this function f subscript y, which is the probability density function of y given x. Now, in case of Gaussian example, as we are assuming that the noise is AWGN, the distribution of y will have Gaussian shape. That is very obvious because we are assuming here and we are assuming it to be AWGN. So the shape of the probability density function of y will also be Gaussian. Now, equation 1 is a general formula. So this equation I am putting it as equation 1. So this is a general formula actually. In the case of Gaussian, it can be example 1. In case of some other distribution, the general formula will remain the same and the details can be a little bit varied. Now, in Gaussian example, so what is this function given by? This function will be given by 1 over root 2 pi sigma e to the power minus y minus ax whole square divided by 2 sigma square. Right. So what we will do is we will draw this function. Along the y-axis will be y. Along the x-axis will be y. Along the y-axis will be this function f or y of f subscript y, y given x, and we will draw this function for a particular value of x1. Right. And the mean of this Gaussian you will get at ax1 when y is equal to ax1. That will be our mean point. So this is the function drawn for a particular value of x1. Draw it for a number of different values. We have to actually draw this function for different values of x. So this is one value of x, x equal to x1 taken, and along the x-axis is y, along y-axis is this function, and we get the peak at ax1. Right. So we have to search for all values of x and find the one which maximizes this function. Now, let us draw it for x2 also. So this is the function drawn for x2, right? I will explain the function bit by bit, so that along the y-axis again, along the y-axis again, this function is there, and along x-axis is y. So we draw this function for a different value of x2. Of course, this peak will come at some different point from this point, because this is for x1 and this peak will come for x2, right? And in general, if we go on drawing these functions and we reach to last value, which is xn, so we will get the peak of the Gaussian curve at axn, right, for this value of xn, and the plotting of the function remains the same. Along the y-axis is this function, the PDF, and along the x-axis is y. Now, what we say is that we measured y, and we say that we measured it equal to y bar at a particular point, at a particular instant of time, right? So our measurement is y equal to, we have different graphs for explaining the distribution of y given x for different values of x. Now at a particular point we measured this y, and this y is equal to y bar. Now this is point y bar, right? At this point y bar, we get the value of this function. I will explain it here. So at y bar, I take the value of this function. I take the value of this function at y bar for x1. For the case of x1, I take the value of this function at y bar for the case of x2. I take the value of this function at y bar for the case of xn. That means I take the value of this function for my measured value which is y bar, and I will find out what is the maximum value of this function. So corresponding to that maximum will that is our estimate, which is x. So let me explain this in a graphical way. So this is my y bar taken. So this is my y bar, and this is my function value at x1. This is my function value at x2. Same y bar is at the same point along all the graphs. This is my y bar value at xn. So in between somewhere I will find I will find y bar, which is actually equal to a times x of MLE, right? I will see that at that point, which is our actually estimate. At that point, y bar will be equal to a of x hat MLE, right? So this particular value where y bar is actually this value is our estimate. That means our function is maximum. So x hat will be equal to x hat, and we will call this as the maximum likelihood estimate, right? For which y bar is equal to ax hat MLE. So this is the procedure of maximum likelihood estimation. Now let us look at what is maximum a posteriori algorithm. Now if you look at the maximum likelihood estimation, we have assumed nothing about the distribution of x. So we don't know what is the distribution of x. So while discussing ML, I have just discussed ML and I have not assumed anything about the distribution of X. But in some cases, I can have some information about distribution of X. For example, if some IoT device is measuring temperature, I know that the temperature cannot be minus 4,000, minus 3,000, minus 5,000. So I have a little bit of information about the distribution of X. I can have the, even in case of radar tracking, the object, I know that it will be somewhere here. So I have some idea about the presence of that object. So I have the information about X. But in case of digital signals, this is not the case, because in case of digital communication, the estimation, the distribution of X is sometimes not available, is not available basically. And you have not taken any measurement at all. So what is map decoding? So you have, I say that you have some distribution of X which is available to you, right? And you have not taken any measurements at all. So what is this distribution? F of sub x, f sub x of x. Now this distribution, this is the distribution of x, which is the PDF, probability density function. The values of x can take. So this distribution explains the values of x which can be possible. Don't take any measurement. So let us find the likelihood where it is likely to find x. So we have information about x, right? And we will try to find out the estimate of x. In that case, x hat max, and we will say that it is max a priori. So this distribution is available to us a priori. With a priori means before taking any measurement. So this will be equal to the value of x for which this distribution, this function gives us the maximum. This is maximum a priori estimation, right? In which we have the distribution of x available, and the value of x for which this distribution gives us the maximum is our estimate. This is max a priori estimation technique. Now, what is XMAP? XMAP means the maximum a posteriori algorithm. So in which we take the y measurements and we try to we check for all the values of x, and we find out this function where f subscript x, the probability of x given y. So we have taken the measurements in the case of map decoding, maximum a posteriori decoding. That means posteriori means once we have taken the measurements, then we are trying to estimate the values of x. Now we know that based on Bayesian rule, we can calculate this. Now our Bayesian will say that, Bayes formula will say that this will be equal to this is likelihood f of y, y given x, f sub y, y given x, f sub x given f sub x of x, and divided by f sub y of y. Now what is this formula? We know, we have already seen in the case of maximum likelihood algorithm, this formula is the likelihood function, and f of x is prior information about x, and f subscript y of y, this is the probability density function of y. Now we can calculate f subscript y of y using Bayesian formula, and this will be given by integral over all values of x, f subscript y given x, into f subscript x of x dx. This is how we can find out the value of this probability density function of y. Now, one thing to note is that this value is independent of particular value of x that we are searching for. This integration over all values of x, this is independent of particular value of x that we are searching for. Right. Now, so we can, in that case, if this is independent of the particular value of x, if we ignore this term in the denominator, then we can say x hat of, in the case of maximum a posteriori algorithm, is equal to f subscript y given x, which is our likelihood function, into f subscript x of x. Now, this is the term which is shown in the dotted line. This is the term which makes map different from ML. If you remember, in the case of maximum likelihood function, only this term was present. There was no term which gives us the prior information about x. This was not present, right? But in the case of maximum a posteriori algorithm, we are multiplying this with the probability distribution or the prior information about the x quantity. But if the distribution of x is now, in that case, there's a special case here. Now, if this distribution of x is uniform, that is, all values of x are equally likely. If all the values can occur equally likely, that means f of f subscript x of x is a uniform distribution. In that case, the estimation of x in the map case will be equal to the estimation of x in the maximum likelihood estimation, right? This is often the case in digital communication. So this is a very common case in digital communication, because you do a very in case of digital communication, you do very accurate source coding, and you apply the source coding techniques, and the symbols will be occurring equally likely, right? So this is the explanation about the maximum likelihood estimation and maximum a posteriori algorithm. Now let us look at a particularly for the case of digital communication. We have already discussed that for a signal transmitted over an AWAGN channel, so either a correlation type demodulator or match filter type demodulator produces the vector. So we have already seen in my previous lectures that we get a vector yi. If you apply even the correlation type of demodulator or a match filter type of demodulator, which contains all the relevant information in the received signal waveform. That means this is equivalent to doing the measurements. Now let us describe the optimum decision rule based on the observation vector yi, which is the measurement basically. The received vector yi is the sum of two vectors xmi. So I is the index for capital N. That means the dimensions of the basis functions, and small m is an index for the number of signal points in the signal set. So yi is the sum of two vectors xmi, the vector equivalent of the transmitted signal, and of course the noise vector. The vector xmi is a point in the signal constellation, and the vector n is an n-dimensional random vector with IID components, identically independent and identically distributed components, each being a Gaussian random variable with mean 0 and variance n naught by 2. Now, since components of the noise are independent and have the same mean and variance, the distribution of the noise vector n in the n-dimensional space has spherical symmetry. Now, what is our goal? We want to we have measured the received signal, and we have obtained a vector yi. So we want to estimate. We want to make a signal detector, and we want to estimate what signal was transmitted. Now we wish to design a signal detector that makes a decision on the transmitted signal in each signal interval based on the observation of the vector yi in each interval, such that the probability of a correct decision is maximized. So that is our goal. So that is the goal in mind with which we will design the signal detection. We will signal detector. With this goal in mind, we consider a decision rule based on the computation of the posterior probabilities defined as signal xmi was transmitted given yi, right, which we abbreviate as xmi given yi. So you can correlate this posterior probabilities as I have explained in my previous slides. Now the decision criteria is based on selecting the signal corresponding to the maximum of the set of posterior probabilities. Now at the end of this section, we show that this criteria maximizes the probability of a correct decision and hence minimizes the probability of error. Now, intuitively, this decision is the best possible decision that minimizes the error probability, but it is clear that in the absence of any received information, in the absence of any received information, the best decision is to choose the signal XMI that has the highest probability. So this I have already this case also I have already discussed, which I said is equivalent to maximum a priori kind of estimation process. But after receiving the information yi, the prior probabilities are substituted with posterior probabilities. So we get these posterior probabilities and the receiver chooses xmi that maximizes this quantity. So this decision criteria is called maximum a posterior probability. Using Bayes rule, I can write this. I have already explained how you can calculate this FYI, which is in the denominator, but this is independent of the particular value of X or M, which was transmitted. So we observe that the posterior probabilities requires knowledge of a prior and the conditional probability, this f of yi given xmi. Some simplification occurs in the map criteria when the signals are equally probable. In that case, the estimate of MLE, estimate of the signal in the maximum likelihood estimation technique will be equal to the estimation of the signal in the case of map criteria. Now, furthermore, we note that the noise independent. So I have already discussed this point. The conditional PDF or any monotonic function of it is usually called the likelihood function. The decision criteria based on the maximum of yi given xmi is called maximum likelihood. We observe that a detector based on the map criteria and one that is based on ML criteria make the same decision as long as the a priori probabilities are all equal, that is, the signals are equiprobable. So that is the concept of actually maximum likelihood estimation and maximum a posteriori kind of estimation and detection. So I finish my lecture here. Thank you.